Consider the following function type. L of x equals mx plus b. You may have also seen in this form y equals mx plus b. These are linear functions. And any function that can be simplified down to m and b, being these are just constants that are given some real number. For instance, I don't know, 5x plus 4. If you can simplify any function down to just this statement here, then it is a linear function. Now these constants m and b are going to dictate the behavior of this graph. An important analysis of function is asking what is the end behavior, or as the function goes all the way to the left and as the function goes all the way to the right. This is the same thing as saying as x goes to negative infinity, goes to the left, and as x goes to positive infinity, to the right. Now, to look at this function, we're going to look at kind of the end behavior and everything, and these constants. And we're going to look at that on a graph here. So I have a graph of mx plus b. These are just linear functions in general. And what I'm changing here is m and b. And just keep an eye on what this graph looks like. So if I change m, I'm increasing m here. So this is 3, there's 5, 6, 7, 8, 9, 10. And going the other way, going down, I'm decreasing it 1, 0, then -1, -2, -3, all up to -10. So you can see as it increases, it looks like this. As it decreases, it looks like that. Let's put it at 1. And then b, let's increase b. And then decreasing b. So that's how what increasing b and decreasing b looks like on the graph. And so the question was what do you notice about the y-intercepts of this graph? So if we look at this y-intercept, we have a y-intercept of 0.75. If I change m, I have a y-intercept of, that's the x-intercept, the y-intercept of 0.75 again. Increase m some more. Y-intercept of 0.75. If I decrease m, still y-intercept of 0.75, increase or decrease m all the way to -10, still 0.75. I can zoom in and that's the y-intercept that I'm clicking on right here. Now if I change b, the y-intercept is now 6.5, b is 6.5. If I go a little bit higher, y-intercept is 10. I decrease b down to -3.25. The y-intercept is -3.25. And so you can see, well, it looks like b is the y-intercept. As you change the function, as you change b, the y-intercept changes as well. Now also, in this thing, if you look at, if I just keep b constant and change m, what you're seeing is that it's all pivoting around this y-intercept, and it's increasing as it gets getting steeper and steeper as m gets bigger. As m gets closer to 0, it gets shallower, like you're not being steep until it is 0, and then it's just a flat line. And then you go the other way, it gets steeper in the other direction. So steep in the very positive, steep in the very negative, and as you get closer to 0, you get very, like, you know, shallow slopes, these low slopes. And the end behavior is the next question, right? If I change b, what happens to the function? So for this function here, the end behavior is as we go off to the negative direction, the negative infinity direction, as x goes that way, the function gets lower and lower and lower. As you can see, the y values are getting smaller and smaller. As you can keep going out more and more, I'm just zooming out farther. We just keep going down and down and down. And as x goes this way, the function just keeps going downward. So we say as x goes to negative infinity, the function, or I should say L of x here for linear function, goes to negative infinity as well. It just keeps going downward on the y-axis. You can see as I go this way, the function just keeps going down. All these values keep going lower and lower. And the opposite happens as we go to the positive direction. As x goes positively, x goes to the positive infinity, the y-axis, or the y values, you can see that it just increases. That means x is going upward along this, or I should say the function is going upward along the y-axis. So the function goes to positive infinity. All the values of y gets larger and larger and larger, and it will just keep going this direction. You could just keep zooming out far enough, keep going up this way. You can see it just keeps getting larger and larger without stop. Okay, now if we change b, this behavior does not change at all. You can see that if b is negative 10, this is still going down, this side's still going up. If I change b to positive 10, this side's still going down, this side's still going up. However, if I change m, you can see that as we get more positive, it's going steeper in this direction. It still goes up to positive infinity. You just zoom out far enough. All these values are covered. You just need to zoom out, and you'll see it does eventually hit them. The same thing is true here. We're still going down to negative infinity. We're going down there faster, but all of these values, you can zoom out way far down. If you zoom out far enough, that point does meet the function. In the other direction, if I hit negative or hit 0, you can see, well, now we flatline. We do not go to positive or negative infinity. We do at 1, and in fact, everything between 1. So let's go to like 0.001. That's hard to see. You can see that you can see if I make it a little bit smaller, it's going to be hard to see, but it still goes up to positive infinity. It goes very slowly to positive infinity, but this does just keep going upward. You have to zoom out far enough, and you'll see that it will be able to reach all of these values. And this side still goes to negative infinity. It's going downward. Just takes a long time. But once I go to 0, I flatline here. This does not go to positive infinity or negative infinity. It just stays right here. In this case, it stays right here on the y-intercept of 10. If, on the other hand, I go to negative m, well, now you can see, well, this, as I go this way, I'm going no longer to negative infinity. I'm going now to positive infinity. So now this is going to positive infinity as you go this way on the left side, the x equal to negative numbers. So as x gets more and more negative, the y values get more and more positive, and it goes up to positive infinity. And vice versa, as x is positive, the function goes more and more negative. So actually, this one now changes to L of x going to negative infinity. That's the big thing I want to show here, is that this m value changes the end behavior of the function, whereas the b value just kind of shifts it up and down. Like that. Okay, if we graph two of these functions, 3x plus 5 and 3x minus 4, then let's go ahead and do that. So you can see here I have graphed 3x minus 5 and 3x plus 4. I'm just going to turn off the previous one. And the only change between these two things is how high they are. They're still going the same direction. The end behavior is still the same. As x goes to positive, the functions go upward, so it goes to positive infinity. As x goes negative, the function goes downward, so they go to negative infinity. But the only difference is just where they intersect the y-axis. And that is at 4 and negative 5. So you can see the green line the blue line intersects at -5, we get 3x minus 5. And the green line intersects at 4, 3x plus 4. All right, so this should tell you, you should have already seen these kinds of things before, but if you haven't, M is the slope, and B is the y-intercept. So this form of the equation is called the slope-intercept form because it uses the slope and the intercept. Now the y-intercept is just kind of an orientation point for a linear function. It just kind of tells you where you start. The slope is really the function's behavior, because you can see as we change the slope, the end behavior of the function changed. If it was positive, it went to positive infinity to the right, negative infinity to the left. If it was 0, it flatlined. If it was negative, it did the opposite. So the slope really changes the behavior. The y-intercept just kind of shifts it up and down. And so finding it is the most important thing to know for a line. Any kind of line you're looking at. Really, a line is just a slope. So how do we find the slope? Well, I'm going to look at these two accounts, so these checking accounts. We're going to ask, what's the average rate of change for each of these things between these 2 weeks? So between week 1 and week 2, we're looking at an average. The average is only a single week between that. So we have, to find an average, we just subtract and then divide by how many numbers or how many periods we've gone between. In this case, we've only gone between one period here. So for account 1, we're going to do final. You do a final minus initial. That'll tell you if you've lost or gained money. Or divide it by 1. So you can see here we get -$500. For account 2, it's going to be final minus initial over a single week has passed in this time frame. And that's going to be $750. Okay, between week 1 and 3, here we've elapsed 2 weeks. So we're going to take final minus initial again. Now we divide by 2 because there's been 2 week time jump. So this is going to be 2,000. Let's see, it's going to be -$750 over 2 is -$375. For count 2, we have 9,000 is the final. 7,500 is the initial. That's going to be 1,500 divided by 2, 750 again. Okay, last one, week 1 and week 4. That's going to be a 3-week jump. The final is 2,900. Oops, I need to subtract it from the initial. The initial is still 2,000. Now we have a 3-week jump. This is 900 on the top, divided by 3 is $300. And then we have 9,750 minus the initial was 7,500 over 3. That's going to be, I believe, 2,250 divided by 3 is 750. And so you can see that account 1 has a rate of change that varies. But account 2, it's always 750. Account 2 is constant. And that's what the slope of a linear function is. It's a constant rate of change. This account 2, I should say, is linear. Account 1 is not linear. It varies so that you can't have a linear function to describe it. Now, how do you find the actual slope? All you have to do is do pretty much the formula that we were doing. It's going to be y2 minus y1 over x2 minus x1. Now, the y values are on top. Y value is the vertical axis on the Cartesian coordinate system. So what this is really telling you is how much does the function rise. And this is the horizontal axis. And final minus initial tells you how much the function runs. So the slope is the same thing as rise over run. That's a good way of thinking about it. And it's going to be very helpful when you're looking at the actual graph to think of it like that, because it'll be easier to find. Now, of course, you'll note that on the bottom of these things, we had always subtracted the weeks. it was always week 2 minus week 1. And so on the bottom would have been x2 minus x1. So our week is the independent variable for our function. It's the x variables. It is the week, which makes sense because you'd think as the dollar amount is dependent upon which week you're talking about. The week is a time variable, and time is pretty much always an independent of choice. So that's going to be our x values. The money would be our y values because they depend on the x. And we can graph them like that using this is week 1, week 2, week 3, and week 4. And account 1 is in red. This was the varying rate of change. You can see it looks not like a line. Whereas account 2 is a constant rate of change, and it looks like a straight line. I could even, draw a line through there. This one I can't do that. Now, the slope is depicted by making a triangle between any 2 points. So, if we just choose any 2 points, let's look at let's look at account 1 first. We choose these first 2 points, then the slope is making a triangle out of this. So you can make a triangle like this, or you can make a triangle going the other way. If I were to do it let's do it in green instead. I still get the same hypotenuse. For both, it's this middle line here, and both of these, this portion and this portion, those are both the same distance, and this height and this height are also the same distance. So it doesn't really matter which way you draw the triangle, you'll get the same answer. And if I choose something up here, then let's actually go between the first and third weeks. So I can draw a triangle like this. And once again, no matter how I want to draw this, I'll get the same answer. The height of a triangle is the rise. The same thing as y2 minus y1, where this is going to be x2, y2. This point here is x1, y1. Same thing is true here. x2, y2, x1, y1. So this is going to be the rise. So y2 minus y1. That's what the height of the triangle is. The length is the run, or x2 minus x1. So x2 minus x1, x2 minus x1. That's how you can find the slope of between any 2 points. Now, if the function you're looking at, whatever it might be, or the relation you're looking at, if it's not linear, the slope doesn't make much sense for the entire set, the entire data set. It does make sense for a linear, function, because this slope is going to be constant no matter which 2 points you look at. For account 2, right, which was a linear function, we found the slope, and it was always 750. In fact, what I was doing before, this is finding the rise over run. That's all I was doing there. So you can see that account 2 is 750 each time. So we can say the slope of account 2, or the constant rate of change, is 750. Account 1, you can't say that. There is no slope because it's changing every single time. But you can calculate a slope between 2 specific points. As long as you're considering only 2 points, then you can calculate this thing. And so what you could say instead is, well, let's look at an average rate of change over the entire data set, over the entire thing. So you could, like, for between 1 and 4, that was the average rate of change for the entire 4 weeks. Or you could say, well, what's the average rate of change between the lowest point and the highest point? That would be this slope here. You can ask a lot of different questions about it, but you're limited on what you're talking about in full slope. So if we look at the slopes between weeks 1 and week 2, Well, that's going to be this triangle here. Okay, so just labeling those y values so it's easier to see what we're looking at. This rise is between 2,000 and 1,500, so it's going to be a $500 rise. Technically, actually, since we're looking at the starting point here, the final point there, the rise is actually negative 1,500. We're going down. And the run, I would always recommend when you're looking at run, consider it always going left to right. So it's always going to be positive. The rise will be either negative or positive depending on if you go up or down. So the rise can be negative or positive. The run, if you do what I'm suggesting here, the run will always be positive, because it's just, I think it's an easier way of thinking about these types of functions. So as we go left to right, we go 2 minus 1, that's going to be positive 1. So the slope is negative 500 over 1, which is just negative 500. Now, between weeks 2 and 3, well, again, we have a run that goes down, and then, sorry, a rise that goes down, and then a run that goes left to right. So a rise between 1,500 and 1,250, that's a negative 250 decrease. And a run, well, from 2 to 3, that's only a one week change. So the slope between weeks 2 and 3 is negative 250. Finally, between weeks 2 and 4, well, same process. Now we're looking at the slope between 2 and 4. It's going to be this triangle here. You can see that we have a rise from 1,500 to 2,900. That's a rise of, let's see, $1,400. And a run now of 2 weeks. So the run is 2. Rise is going to be positive because we're going upward. So the slope is 1,400 over 2. That's a $700 change per week on average. Now, I want to look at different kinds of functions, because there's a lot of different linear functions that we've been looking at. I just want to look at them specifically to talk about their features. So first off, we have if m is greater than 0, okay, then this is the kinds of functions we get. Just you know, as some sample ones. You can get many different ones, but these are 3 sample versions. And this, as you go left to right, the function goes upward. Left to right, the function's going upward. Left to right, the function's going upward. This is an increasing function because f of x gets larger, or I should say L of x here gets larger and larger. As x goes to positive infinity, L of x goes to positive infinity. We always like read left to right, so that's the reason why we're looking at as x going to positive infinity, the function going upward or to positive infinity, that's an increasing function. Now, all 3 of these linear functions, in fact, all linear functions, but all 3 of these specifically, have a domain of everything. You can see there's no break in what this value is. This one looks like it might not reach all the values, but of course it does. You just have to zoom out far enough, and like a value way over here this function will eventually cover that value. The range, you can see, well, it's going to go all the way up to positive infinity. This goes very slowly, but it does go there. It also goes downward infinitely as you go leftward instead of going right. Going left, it goes down to negative infinity. The end behavior is that this function goes up to positive infinity, goes down to negative infinity. Up to positive infinity, down to negative infinity. Up to positive infinity, down to negative infinity. That's the end behavior. So the range is everything. And like I said, the end behavior is as x goes to positive infinity. Well, we already know this is an increasing function, so it goes to positive infinity. And as x goes to negative infinity, goes the other direction. As we go leftward, the function goes down. And that's what this one is telling us. L of x goes to negative infinity. So in behavior, you can commonly use these arrows to show the in behavior where the function's going, because it's going to go in some direction eventually. So these arrows help show that. Some functions don't have in behavior; they actually change, and we're going to look at those later on. But these do go somewhere. So if now m is less than 0, you can see these functions are m less than 0. As you go left to right, the function's going downward. It's going downward, and this one's going downward very fast. These are decreasing functions. Or, of course, as x goes to positive infinity, left to right, L of x goes to negative infinity, it goes down. The domains of all these, once again, negative infinity to infinity. The range, you can see that we of course go down to negative infinity, and it actually will go as you go right to left. The function goes upward, and that goes to positive infinity. That means that our in behavior, as x goes to the right, the function goes downward. Goes down to negative infinity. As x goes to the left, or to negative infinity, L of x goes to positive infinity. It goes upward this way, downward that way. Upward this way, downward that way. Upward this way, downward that way. That's the end behavior of these decreasing functions. Okay. Now, we're assuming that k is some real number. Of course, k can't be 0, because if m equals 0 over k, if k is 0, you have what's called an indeterminate function. You cannot find this. But if you have 0 divided by some number that's not 0, then this just is 0. And that makes these linear functions flatline like this. And that is a constant linear function. It's always one value, whatever that value may be. So this is going to be, let's say this is going to be, or let's look like this. This is mx plus b. Well, m is 0, so we get 0x plus b. But that's just b. So you could also say it, this is typically how you'll see it written, as y equals b, or L of x, or some function notation equals b. But it's just the y-intercept. Every point on here has a y value of something here, and then b. This point has something for the x value, and then b for the y value. Everything back here as well. That's all it is. This is also b here for this linear function. So the domain, you can see it does go left and right continuously. So the domain is everything, because this goes all the way that way, all the way that way. So all of these values are covered here. The same thing is true for this one. The range, however, it never gets past this one value of b. All the y values on every single point here is b. So that means the range is the singleton set b. It's just a set with one element in it. Now, the end behavior is different, because we do not go upward or downward either direction. We stay constant. So you can say there's either no end behavior, or it's just a constant at b. Something like that, to get across that it doesn't go upwards or downwards. It just stays flatlining there. It never changes that. Okay, the final one we haven't talked about is, of course, when we have a division by 0. Now, k can be any number here. If it's 0, you get an indeterminate one, but a division by 0 here is going to be an issue. We cannot do this. So m is called undefined. And when you have a division by 0, this results in a vertical line. It kind of makes sense, because a division by 0, if you were to think about it using what's called limiting values, it goes to infinity almost. It can't equal infinity, of course, because infinity is not a number, but it goes to infinity. And that, if you were to look back at when we were adjusting the function, as m got larger and larger and larger, the function got steeper and steeper and steeper until it looked like it was almost vertical. If m gets very, very large, it looks very, very vertical. Not quite, but it does look that way. Now, vertical lines do not pass the vertical line test because they are themselves a vertical line, right? I can draw a vertical line here, and it crosses this one infinitely many times. So that is not a function. So we cannot use this this notation for it. It doesn't work. Instead, we use this description: x equals a for some real number. Of course, this one is 0 here because this is on the x-axis, but a is just some x value where the vertical line hits. Because the domain is only a. It's the singleton set a. It's the only value that's in the domain. It doesn't go left or right at all. It stays in that single value. The range, however, is everything. It does go all the way up and all the way down to negative and positive infinity. And for this function, there really is no end behavior. It doesn't go left or right at all. So you really would say nothing here. Okay, give this a try in number 1.